Welcome to our presentation. Today that's Lukas Ehrmann and myself, Kohlen, would like to present the result of our work, an evaluation framework for blockchain-based public key infrastructures. We'd also like to take this time to thank our supervisors, Feng, Cheng and Pejman Najafi, who supported us in this. So let's get started by looking at our motivation and research goals. So new clients are being added to the internet every day. This is, for example, due to trends like the Internet of Things, but just also the constant growth. And these clients usually require secure communication and therefore also authentication. This authentication right now is often handled through public key infrastructures, most notably the X509 public key infrastructure, or short PKI. However, this PKI is not without failure. Weaknesses in it often cause unauthorized certificates, for example, because a certificate authority is compromised or goes rogue. This is also caused by sometimes poor organizational or technical security of certificate authorities. Another issue can occur when an unauthorized certificate has been noticed and a revocation has been issued, but the certificate status information is unavailable to the client at the time of validation. An idea has developed to use public ledgers to address some of these issues. To our understanding, this has first been proposed by Fromknecht back in 2014. With this work, we want to answer a number of research questions. The first is, what requirements must a blockchain-based PKI fulfill to be useful and successful? We then want to apply these requirements to the proposed designs and see how well they fulfill them. And finally, we want to see which open issues remain unsolved by the proposed designs based on our requirements. Let's get started by looking at the evaluation framework we have created. We have split this into requirements and architecture decisions, where requirements are basically abstract requirements that any design needs to fulfill, whereas architecture decisions are based on the proposed designs and what they've decided in their development. So the requirements are mostly based on a study from 1996, back when the original PKI, which is now so widespread, was designed and built. And we have adapted these requirements for today's state-of-the-art and use cases. So for any system to even be considered a PKI, it must fulfill a certain baseline. The system should be able to sign and validate certificates and must have a baseline of security, so it's not just possible to create a certificate for any identity and for it to be considered valid. Beyond this baseline, we get into the more complicated detailed requirements. The first requirement is trust by the community. So because we usually trust into the root certificate authorities, they can then transfer this trust to intermediate authorities and then to the leaf certificates, which we can trust again. Any proposed design must also be able to transfer trust in this way. And also the system must have initial trust by the community for its setup to be successful. The second aspect is ease of use. The more widespread the system is used, the more secure the whole infrastructure becomes. So it should be easy to obtain a certificate, and it should especially be easy to validate a certificate. However, no matter how secure the system is, there will always be some unauthorized certificates. And if this happens, the certificates need to be revoked. The system should provide the ability to revoke certificates, and it should be able to transfer the information of revocation from the revoker to all other participants of the system in a fast and reliable way. Then we get to the requirement of user authentication. So before obtaining a certificate for a certain identity, the user needs to prove that they own or are that identity. So this is basically the issue of user authentication. How do they provide this proof? And also, how do they prove that they are who they claim to be before, for example, issuing a revocation? Then we have the requirement of privacy, which is twofold, and we're going to look at it on the next slide. Before that, we also have the requirement of certification policies. So any certificate should not just be a wildcard, it should be limited to certain use cases. Currently, this is implemented through the X509 standard, which allows limiting certificates to use cases like software signing or domain validation. So if the X509 standard continues to be used, that's of course covered. But if a new standard is proposed by these designs, then it must also provide some way to limit the uses. Then we have added 3 requirements beyond the study from 1996. based on how blockchain-based PKIs work. There's first of all the requirement of scalability, so that the system must be able to work under real-life workloads, so the millions of certificates that are created and used every day. It should also provide transparency over the certificates. This doesn't just apply to blockchain-based PKIs, but PKIs as a whole. And this has already been established through, for example, certificate transparency logs, which provide a public log of all created certificates. And for a certificate to be considered valid, it must be entered into this log. Last, we have the requirement of change incentive. So this is a bit of a meta requirement because it can also be fulfilled by fulfilling all other requirements better than the current PKI. Because obviously then the system has advantages and there's an incentive for change. Alternatively, there can also be direct incentives. For example, since we're talking about blockchains, there can be a financial incentive for the root certificate authorities to switch over to the system. Maybe it's cheaper to run for them. Maybe they can obtain money in some way. So let's now look at two requirements in detail. The first is privacy. So as said, this requirement is twofold. First, we have the privacy of certification. In some use cases, the creator of a certificate does not want to advertise the identity it certifies, for example, the domain. This could be because, for example, the connection between domain owner and domain name can reveal some secret information. On blockchains, it's typically implemented by only storing the hash of a certificate on the chain. The second aspect is the privacy of validation. This means that the certificate never leaves the client during validation, so that the identity that is being validated is never revealed to a third party. Another advantage here is also that the validation is more distributed, so it's done on the individual clients and therefore less prone to a single cause of failure. The second requirement is scalability. And the second requirement we want to look at in detail. So we've split this into three parts. The first is performance. This mostly pertains to how much computational power is needed to run the system. Mostly affects the time it takes to complete certain actions of the PKI. For example, it's acceptable if the issuing of a certificate takes a few seconds or maybe even a minute, but the validation of a certificate must be done in just a few milliseconds. Otherwise, the overhead to secure connections is too high. The second aspect is storage. So obviously, the millions of certificates need to be stored somehow or validated somehow. And this requires some storage on the systems running the blockchain. And since it's a blockchain, every participant with a full copy will also need the same storage space. So it needs to be ensured that this storage cost does not become prohibitive. And finally, we have the aspect of cost. This is, of course, influenced by performance and storage, since these also incur costs. But there can also be other factors. For example, some systems are based on Ethereum. And for Ethereum to run smart contracts, gas or ether needs to be paid. So these are the requirements. And now we're going to look at the architecture decisions. The first architecture decision concerns the scope. So does the proposed system want to replace the current PKI? Or does it just want to extend its functionality? The option of replacing it, or as we call it, alternative, usually comes with a drastic change to trust structure or the trust anchors. And some of these systems also combine DNS and PKI. So only the owner of a domain can then also request a certificate for it, for example. So these are, of course, a drastic change. The other option is that of an extension. So it just extends the functionality of the current PKI, for example, by introducing new steps into the certification and or validation. This has, for example, in the past happened with protocols like OCSP or certificate transparency. With certificate transparency, you need to enter all certificates into a public log before they're considered valid. So that's a step in valid certification. And before a client accepts the certificate as valid, they make sure that this certificate has actually been entered into the log. The second architecture decision concerns the trust structure. So there are two main options here. The first is that of an hierarchical trust structure, which is similar to the current PKI. At the top, we have the root certificate authorities, below them the intermediate certificate authorities, and at the end, the leaf certificates. So any design incorporating this is more similar to the current PKI which can make transition and incentives easier, for example, because the root certificate authorities get to keep their role and therefore their business model. So the initial trust is also there because the trust stores on the clients can continue to be used in some variants. The other option is that of a web of trust. So this means that each individual client trusts some other clients, and when a new untrusted client is encountered, you try to build a path of trust through other nodes. And in this way, there is no reliance on trusted third parties like root certificate authorities. And the trust settings can also be more granular because you can, for example, configure the maximum length for a path of trust. The last architectural decision concerns the blockchain. The first option is to use an existing blockchain, like, for example, here listed Bitcoin, Namecoin, or Ethereum. This has the advantage that these blockchains have been proven to work and tested for several years. There's, of course, a huge financial incentive to find a weakness which allows you to break this blockchain. And they also have an existing pool of resources, which can prevent some attacks, like a 51% attack, where you have a majority of the computing power in the blockchain and can therefore manipulate it. The other option is that of a custom blockchain. So here you create your own blockchain design based on established standards, but you can, of course, also adjust the feature set to PKI requirements. And for example, you can design transaction prices around PKI use cases. For example, ensure that validation is free, set a certain cost for certification, and so on. So these are all of the requirements and architecture decisions we've included in our framework. And now Lukas is going to apply them to some proposed designs.
Thank you, Kai. Let us now have a look at existing implementations on the public ledger, how they decided in terms of key decisions, and how they fulfilled the requirements. We have analyzed 14 different approaches from the year 2014 until 2021. The first criteria we analyzed was the scope of the paper. Some provide an alternative to the current PKI, some provide an extension. The trust structures were mostly based on hierarchical ideas. A hybrid model was proposed by only a single author. And last but not least, we had a look at the blockchain. Most of the proposals used Ethereum as a basis, since it provides the ability to execute logic with the smart contracts on-chain. We have evaluated these proposals based on the presented 11 requirements. For now, we want to share the evaluation of 5 of them, which we assume to be most important. A tick means that the criteria is fulfilled. The heavy ballot X means that the criteria is not fulfilled. A box means that it is partially fulfilled, and a dash means that it was not addressed in the paper. A tick in validation from Knecht, for example, means that a user of this proposal is able to validate a certificate without the need of revealing the owner of the certificate to a third party. At the same time, privacy of certification for from Knecht was not fulfilled, since the owner of a certificate needs to share the whole certificate to the ledger. In terms of scalability, we're sharing here the fulfillment of the requirements in terms of performance, storage, and cost. Fromknecht, for example, did an evaluation on the scalability and performed reasonable values for performance. The authors of this proposal made as well thoughts on storage and presented an approach on how blockchains could continue to exist while storing the massive amount of data. Costs of this approach were not considered from the authors. What is rarely considered, as you can see, are the privacy of validation in the first column and the cost aspect of public ledger solutions in the last column. With that, we want to discuss our results, provide an overview of open issues, and come to a conclusion. During our research, we identified those 3 main open issues. The public ledger PKI should have a scalable design. Limitations of performance, storage, and costs shouldn't apply to any solution developed in future. This should be considered in the design in future and thereby as well be evaluated. In addition, further research in the area of foresight should be done on how PKI systems are currently used and what requirements they must fulfill in the upcoming years. As a second issue, we identified the need of holistic solutions. The idea thereby is not only to consider the scalability aspects, but clarify and document all decisions made which led to a certain design. This makes comparison and decision-making in the future easier. As a third issue, we identified research in the field of transition. Research could be done regarding on how a transition of a worldwide and long-term use system can be handled. Research on how to incentivize the transition for the entities or in the current PKI needs as well to be conducted. Kai introduced at the beginning our 3 research questions. I would like to conclude our presentation now by answering those 3. The first question was, what requirements must blockchain-based PKIs fulfill to be useful and successful? We have presented a framework by doing extensive research which can be applied to all blockchain-based PKIs and describe them in a degree of detail which makes them easily comparable. The second question was, how well do proposed designs fulfill these requirements? Therefore, we have shared our comparison between multiple solutions from different areas. If you're interested in the full comparison, we encourage you to have a look in our paper. And the last and third question was, which open issues remain unsolved? These were the points I've just shared with you, including the scalable design, more holistic solutions, and research in the area of the transition. With that, we want to thank you for your attention and are happy to answer any open questions. If you're interested in our research, you can reach us by mail.